I'm from Japan. Today, I will be presenting our study title, Elucidating the Inspirational Practice in School-Based FabLab Activities and the Development of Independence. This research explores the inspirational practice that drives student engagement in school-based FabLab and how these experiences contribute to their autonomy and skill development. FabLab, first conceptualized at MIT by Jushin Field in 2012, a digital fabrication workshop that promotes hands-on learning. Similar model is worldwide, such as Open Design in Berlin, which integrate open source design with urban planning. In Japan, school-based FabLab or FLab are increasingly used STEM STEAM education for students of directed learning and technical proficiency. Despite their growing adoption, the research explore what motivates students to engage in these spaces. Understanding these motivational practices is essential for designing effective learning environments that sustain the engagement and skill development established. In Japan, education consists of primary, secondary, and higher education. Compulsory education includes 6 years of elementary and 3 years of junior high school, followed by high school. Our study focused on school-based FabLab implemented in upper secondary school, where students explore self-directed learning through hands-on making activities. This study aimed to answer 3 key questions. First, what activity do students undertake? Second, how does FabLab participation for autonomy? And finally, what motivates students to participate and persistence? By addressing this question, we hope to gain insight that will inform the better design of FabLab-based learning environments. We conducted a qualitative study with 3 university students who had previously participated in FabLab activities. To collect data, we used 2 methods: activity logs. Students recorded their engagement in FabLab project. Second, semi-structured interviews. We explored their motivation and learning experiences through in-depth discussions. For data analysis, we applied 2 approaches. One, classification of activity types and triggers. Based on Ichikawa's 1998 framework, we categorized different types of activities and what motivated students to engage in them. 2, scat qualitative analysis, a structured 4-step coding method that helps us extract key motivational factors. This approach allows us to gain deeper insight into how students interact with FabLab and what drives their continued participation. Moving on, I will discuss how to interview. During the semi-structured interview, we showed participants photos of their past activities in FWRC. This approach helps them recall specific moments, reflect on their experiences, and describe their learning motivation in detail. Then let me introduce data collection. To structure our interviews, we developed a tool called the Table Learning Activity Log, which helps categorize student engagement patterns in FabLab. For classifying motivation, we use Ichikawa's 1998 framework, which defines different types of learning motivation. This allows us to identify the key triggers that drive student participation in FabLab. We also refer to Niwa et al. 1998, who categorized activity into 6 types, such as skill-oriented and team-based activities. This framework provides valuable insight into how hands-on activities contribute to both skill development and autonomy. Furthermore, I will explain how to analyze. To analyze students systemically, we applied coding and quantification to the activity log data collected from interviews. Each recorded activity was categorized into preferred classification and relevant engagement factors were extracted. This allows us to convert qualitative responses into numerical data, making it possible to perform statistical analysis. The results provide insight into how different learning motivation and activity types correlate in the favorable environment. To analyze how students develop understanding in favorable, we applied SCAT Alternate 2022, a four-step quality analysis method. First, we identify key phrases from the student's statement. Next, these phrases were paraphrased into simpler terms. Next, we extracted explanatory concept. Finally, we conceptualized overarching themes to interrupt learning patterns. This structured approach helps level how students recognize challenges, justify action, and engage in problem solving within FabLab. Analysis result, linking object with findings. To effectively present our result, I will explain how each research objective guided our analysis. First, for object 1, we categorize student activity types using Ishikawa's framework to better understand their engagement patterns. Next, object 2, we conducted individual analysis to examine how favorable activities influence students' skill development. Finally, object 3, we applied SCAT analysis to analyze interview data and identify key factors that motivate students to participate in favorable activities. Through these methods, we aligned our data collection and analysis with the 3 research objectives, leading to mindful insight into student engagement and learning outcomes. To understand what motivates students in less level, we categorize their responses using Ishikawa's 1998 learning motivation framework. Most common motivation type was fulfillment-oriented learning, 44%, meaning students engage because they enjoy the process. Our students described how seeing their ideas take shape kept them motivated, highlighting the existence of hands-on creation. Other motivation increased practical-oriented learning, 22%, where students valued real-world application, and relation-oriented learning, 15.6%, influenced by peers and teachers. In contrast, reward-oriented learning and self-esteem-oriented learning, 44% each, suggesting that intrinsic motivation drives S-level participation more than external incentive like grade or competition. Understanding this pattern is key to designing learning environments that foster long-term engagement and deep learning. To understand how students engage in S-level, we analyze their activity types by comparing observed and expected values. The most notable finding the skill-oriented activities was significantly higher than expected, residual equal to 0.15, suggesting that students prefer hands-on tasks that build particular skill aligning with the favorable approach. For example, one student finds a 3D modeling skill to create more complex designs, demonstrating how learning by doing foster engagement. For example, meanwhile, challenging activities and independent work were relatively high, while term-based and expectation-driven tasks were slightly lower, indicating a preference for self-directed learning over structured group work. Overall, these structures confirm that intrinsic motivation drives stable participation, emphasizing the need for favorable experiences that support skill building and autonomy. Through favorable participation, students showed significant growth in the key skills, particularly autonomy plus 6.09 digital, executing skill plus 5.48, technical skills plus 6.09, and questioning skill plus 5.18. This suggests that FabLab boasts the independent learning and technical proficiency. Autonomy had the highest residual, indicating the student took initiative in their learning. For example, one student defined their project to push their own limits, demonstrating self-driven learning. Execution skill also improved plus 5.48, suggesting the hands-on experiences enhance students' ability to manage tasks and project effectively. Simply, technical and questioning skills were notably high, reinforcing the student gained particular expertise while developing a habit of inquiry. In contrast, teamwork and communication skills were lower than expected, suggesting that FabLab emphasized self-directed learning over collaboration. These findings confirm that FabLab provides an effective environment for students to develop technical expertise, problem-solving skill, and independent learning. To understand what inspires long-term engagement in FabLab activities, we conducted a qualitative analysis using SCAD. Through this structured approach, we extracted 5 primary inspirational factors that motivated students to sustain their participation. First, invitation. Many students began engaging FabLab activities because they were invited by peers. Peer influence played a crucial role in encouraging initial participation. Second, instruction advice. Some students were motivated by recording guidance from teacher or mentors. This mentorship helped them develop their own learning goals. Third, collaboration. Engaging in group activities and working alongside others motivated students to acquire new knowledge and sustain their environment. Fourth, discovery. Many students were inspired by curiosity, seeing others using technology such as 3D printers spurred their own interest and encouraged them to try new activities. Finally, invertibility. Some tasks were unavoidable step in processing their project, which led to a sense of responsibility and persistence. To understand how students develop autonomy in FabLab, we analyze their experiences using SCAD. The results highlight 2 key factors. Environmental management. Students reshape their learning spaces to fit their needs. For example, ICT lab evolved from a club space into broader learning environment, showing how students take initiative and adapting their surroundings. Next. Collaborative knowledge, peer interaction, enhance engagement and learning. One student noted that learning programming alongside peer and made make the experiences more enjoyable and motivating. These findings suggest that FabLab foster autonomy by encouraging students to actively shape their learning environment and collaborate with peers and sustain engagement. Our findings indicate that FabLab promotes self-directed learning, but challenging remain. Limited collaborative activities suggest the need for structured teamwork initiative. Our studies show that FabLab effectively supports self-directed learning by leveraging inspirational factors. Students serve in developing autonomy and technical skills through hands-on activities, reinforcing intrinsic motivation. However, certain challenges must be addressed to maximize their potential. First, collaboration was limited. While students excel in independent projects, teamwork initiatives were lacking. This suggests the need for structured group activity to enhance peer learning. Second, stress management strategies were underdeveloped. Some students struggle with step back in their project, highlighting an opportunity to introduce resilience training within FabLab settings. Finally, engagement level varied among students. Personalized learning pathways may help sustain motivation over time. Addressing this challenge can further refine FabLab as effective environment for fostering both independent and collaborative learning experiences. Thank you for listening.